Hello, I'm Justin Bruner, PennDOT's Bridge Asset Management Section Chief and Asset Management Engineer, and today we're going to talk about the value of bridge preservation. So what is preservation? Well, the dictionary says it's the act of preserving something. I'm not sure they could be any more clear about that. I don't find that to be entirely helpful. But their second definition says the state of being preserved, especially to a specified degree. Now that I find helpful. Okay, so preserved into a specified degree. So when we translate that to things that we can utilize in our industry, what that means is maintenance, and specified degree means good condition of the asset. So preservation is not just the activity, but it's the timing. So preservation activities include epoxies, bituminous overlays, joints and seals, or latex or polyester modified concrete for bridges, crack sealing, seal coats, and thin overlays for pavements. But the important part is it's not the activity itself, but when you do it. So if you see up here on the upper right where that purple arrow points to that purple box, you can see that the preservation activities really should happen earlier on in the asset's condition, not necessarily life, but condition. So if an asset's in good condition, these lighter treatments tend to last longer and preserve the asset. And that's really what we're going for here. The concept of a lower cost, lighter treatment earlier in life makes the asset last longer, which is exactly what we need in today's current financially constrained funding scenario. So preservation is an integral part of lowest life cycle cost programming. So it is both a treatment and a timing, right? And it's consideration for the whole life of the asset. So we're going to talk a little bit more about this later, but the concept is we can't look at the short-term goals. We can't look at, say, hey, we're going to do change the condition of X number of bridges or Y number of miles of roads in these 3 years at the cost of other things. We have to get away from that short-sighted mentality and start looking at the long-term performance of our overall network. And we start talking about treatment and timing, that's lowest life cycle cost. And you can't talk about lowest life cycle cost without the concept of risk-based prioritization. Now, the asset management divisions have put out a infographic here. We've talked a lot about this. And basically all these fancy terms come down to lowest life cycle cost means that you need to do preservation early and often, and you prioritize your largest assets over some of your smaller ones, because that's where the risk comes in. You can't afford to replace an interstate every so many years, or you can't afford to build a brand new billion-dollar bridge and then let it do nothing and let it degrade to almost closure. You need to invest in those maintenance activities to make sure it stays in good condition for the life of the asset. So let's go over this for the bridge example, right? There's a lot of differences in treatment and timing, so let's talk about this. In Pennsylvania, we've seen that there have been some bridge decks that have, from inception to poor or worse condition in 35 years. It happens, not often. I mean, there's a few examples, but it does in fact happen. All right, so it's likely that nothing ever happened to it. Could have been a poor construction quality issue, whatnot. But this is part of the example. If that particular deck had an epoxy put to it early on in life, it would have extended its life, increased its condition slightly, right? And that green line would then follow and parallel that black line the whole way down. But really, we don't really do that often because we tend to do an intervention at that 15 to 20 year mark historically, and we do a latex modified overlay. We hydrodem and put latex down. That extends the life of the deck significantly. That's a good thing, right? And it didn't cost a whole lot. And then in the past, what we've done is let that ride and come back through with the rehabilitation. And this has been sort of our traditional approach to it. It's sort of a hybrid between do nothing and absolute all maintenance, or I should say all qualified maintenance. And really what we need to start thinking about is a different approach to the second part of this, right? We really, that time there that we're getting with our current approach can be modified slightly, and we can look at this as doing multiple latexes instead of waiting for that rehabilitation. It's a change in methodology, goes to lowest life cycle cost concepts, but what that gets you is significantly longer time for not a lot of money. And that's the really important part here. You can manage that asset and let it extend its life through time for not a lot of dollars. So it's lowest cost over the life of the asset. So in a very simplistic comparison, and yes, if you're a bridge person, you'll see some errors in this, but I'm trying to keep this simple for everybody. If we look at, relatively speaking, a do-nothing approach in the blue box versus the all possible maintenance approach, which would be the green box, you're looking at about a 57% decrease in the cost of ownership over the life of the asset. If we say that another way, that's 50% more budget. That's huge, right? That's like, wow, we can do this. But let's be honest, we haven't performed the lack of maintenance on everything, right? We're somewhere in the middle now. So we're never going to see that 50% more budget come to life, right? But what we can do is extend the life of our current assets a little longer, be a little bit better with our investment strategies, and we can do a little bit better than what we are doing. We've been doing pretty good lowest life cycle cost project selection, but there's a little bit of room to do better. So why all of a sudden are we talking about this stuff, right? So what was wrong with the way we were doing things before? Well, nothing, until we realized that we have gotten away from a flat funding scenario and now we're in a reduced funding scenario. So even there's a big discussion about whether there may be more money on the horizon or whatnot, we are so underfunded, it's not funny. We have one of the largest networks, right? And we're at the edge of the rust belt. So our stuff degrades much quicker than everyone else's. And this is a problem because we don't get the life out of it. So we have a huge transportation cost and not the revenue to cover it. That's a big problem. I mean, we have about a $6.9 billion budget. We have about a $2 billion letting schedule, but we're facing an $8 billion shortfall. I mean, that is enormous. We are really, really financially constrained. And we need to figure out the best ways to do what we can with the money we have currently and hope in the future that we get some additional revenue. Otherwise, we're going to make some very difficult choices. So when we had flat funding, a lot of the state and federal metrics looked at poor, right? So measuring poor leads to managing poor. And we did a bang up job of taking care of that. If you look at the graph on the left, we were approaching 6,000 poor bridges. We called them structurally deficient back then. And over the course of almost 10 years, we reduced that down. Did a really good job of that. And we communicated that through count. But as we improve our ability to understand and manage through life cycle costs, we realized that one, count's probably not the best way to do that. So if we start looking at deck area, the graph on the right with the very solid lines shows the same information, but in terms of deck area. And you still will see a very solid progression downwards, so we did a good job with that. But the problem is we're running out of money, right? We don't have the money to keep that methodology up. And so if we continue on, we're going to reverse that trend. In fact, we're going to reverse that trend regardless. So what we need to do is create new metrics that are revised to look at the whole picture. We need to start talking about things not just in poor, but in good, fair, and poor, and for bridges, for deck area. So how do we do this? Well, this is all part of asset management, and almost anyone can do asset management. It's not all that difficult. Any owner, whether you're a municipality, whomever, if you own assets, you can perform asset management because you likely have an inventory. You have condition data from your inventory. You have performance, which means you know how they degrade over time. If you don't know that off the top of your head, it's pretty easy to come up with a rudimentary calculation to show that. You can also spend a lot of time and effort developing very custom curves for each individual asset. That's the best way to do it. It's also the most expensive, but it does get you very accurate results. You have treatments. You know what projects are costing. You can go through and mine that data and find out what each treatment costs you. And then you have costs. So the combination of all those with risk is your core tenets, right? Include that with lowest life cycle cost methodology and a system, and you can get lowest life cycle cost programs. Now, you don't necessarily need a fancy system like BridgeCare or DTIMS from Dayton, right? You can use a spreadsheet if you need to. It's not that hard to do if you have a small number of assets. But when you start to get massive amounts of information, 25,000 bridges, 40,000 miles roads, and you need big systems that are capable of performing big calculations to get yourself to lowest life cycle cost. All right, so let's look at this a little more in detail. The graph on the left shows what happened in the past from the worst first methodology, i.e. let's take a look at and focus on all the bridges that are in poor condition or close to being poor, and let's try to replace those. Well, if we continue that methodology and put it into our systems and forecast the future, you'll see what happens. Our number of poor goes up a lot, largely because we're just running out of money. Now, it's interesting to note that between the two red lines on the left graph, we actually received additional funds outside of our normal budgeting operations to achieve that goal. There was federal incentives, there was a state program, and then we actually did a little debt financing to make that happen. So when we take and utilize that methodology and forecast that out, you can see that we just don't have the money to keep doing that. Now, when you use the exact same dollar amount and use a different methodology, now you see the concept of lowest life cycle cost and a preservation first strategy. You get a little less poor and a lot more fair. So if we just compare these side by side, you'll see that it's not an insignificant savings just from changing our methodology. So that's really exciting. So asset management has been around for a while. It was first mentioned in the late 80s in an FHWA report, or so says Wikipedia. I haven't seen that particular reference. But it was really began officially in New Zealand in about 1996. They're the first ones to officially adopt it as a methodology for planning and programming. Since then, it has grown tremendously to the point where the United Nations actually offers free courses on asset management for underdeveloped countries, so they can use the resources to the best of their ability. So it's really become mainstream. It's really the way the world is moving towards programming projects. And the reason I put this red report here in the middle, the Data Integration Pennsylvania Experience, in there, that references, it's a report from 2004. And that references a 2001 report that then references some work done in the mid to late 90s, showing that Pennsylvania really was on the forefront of asset management at the time. We're doing a really bang-up job with data, particularly in pavements, and we had some real great plans that were captured in this report. Unfortunately, we didn't execute some of those. We got a little sidetracked, but I believe that if you read that report now, you'd see that we're very much in line with what we were trying to do then. So I feel as if we've kind of come full circle. So the industry, it's become rather robust. There's an actual formal knowledge base. It's called the Institute of Asset Management. They offer certificates and degrees. And this is actually the basis for many of the FHWA requirements through MAP 21 and the FAST Act. So these guys sort of teach the concept in the class, and it's a really, really great program. So if anyone's in a municipality or other owner that wants to learn about this, I highly recommend checking this out. These guys are really good. So in terms of implementation in preservation and lowest life cycle cost, what worked well? We have some pretty proven cost savings. We run our bridge and pavement models into the future. We can show that there's a fair amount that can be saved by maintaining that lowest life cycle cost methodology. So that's exciting. We're also getting into intergenerational transportation equity. Yes, that's a mouthful. But what that's the industry term for pretty much saying that we're going to solve today's problems with today's money. So you try not to kick the can down the road. You try not to put off things that you know are going to cost more later. You try to solve them now and it costs less. And there's no impactful negatives to implementation, right? So some of the old metrics are always going to show not showing the best light, but quite frankly, they're the old metric. And if you keep following newer metric style, it'll all work out. So we're pretty happy with all this. What hasn't worked so well? Well, we're using a whole bunch of systems throughout the DOT, and for things that no one envisioned them being used for. So there's some data cleansing issues, some system utilization issues, right? We're trying to pull data from everywhere, and it's difficult. Not all that data is set up to be used in that manner. So there's, there's a fair amount of learning curve there. There's data cleansing. There's, education on all sides. What people were using a data field for, and it's really important for us so that we know what the condition of the assets are, so we can project that into the future. In terms of the systems themselves, this has been incredibly challenging. It's basically a new field. There have been implementation issues with both our commercial software and our custom in-house software. and utilization issues, right? So we have to get people trained up. There's always updates happening. It's just incredibly difficult to implement a system that allows 11 different districts to function in 11 different ways while still sharing information. So that's just really one of the most challenging things we have about all of this. In terms of lessons learned, implementation statewide is still ongoing, right? So we're still in the learning phases of how we're going to roll this all out. We probably should have utilized change management a little sooner than what we did, but nonetheless, it's going, I would say, as best as we can expect. Again, those data business metrics will suffer. That will encourage some resistance, which is unfortunate. But the reality is, as we move toward new measurements, those measurements are a more accurate reflection of our overall inventory, and hopefully that will become adopted in standard here before too long. In terms of cost benefit, this is really challenging. Like, how do we put costs associated with system implementation going to lowest lifecycle cost? That it's just a really difficult question for us. So really, in the end, I think the best thing to say is that in implementing this, our happiness is super high, right? We can show that there's benefit in doing all this. We have a bunch of new tools at our disposal that really help us manage our assets better. So I would say that we're just ecstatic with what we have. And COVID-19 implications. Since this is software, we were allowed to work on this at home over the slowdown. And actually, one of the things that we did during that period was to be able to show the financial impacts to our network based on revenue forecasts, right? So we were really unsure at the time how much revenue we were going to lose because of all this. So we were able to, on a monthly basis, update our forecast to show what our impacts were. So that was just really, really exciting for us. So with that, that concludes our discussion. And I'll take any questions. Thank you.
Good morning. I'm Tim Correa. I'm one of the Assistant Chief Bridge Engineers for PennDOT working out of Central Office in Harrisburg. I want to thank you for coming to this session. Following up Justin's presentation on the value of bridge preservation, we will have two districts that will present their experiences with various treatments. With the fiscal restraints today, we all need to extend the life of our bridges with the best treatment that fits the situation. PennDOT has put considerable effort into determining the best strategy based on the deck condition. So how did we get here? A need was identified to develop a comprehensive and consistent statewide deck overlay strategy for deck preservation. A meeting was set up. The 11 districts were all tasked with investigating what methods they've been using to preserve their bridges. We asked them to look at the costs, longevity, effectiveness, and to identify the advantages like ease of installation and disadvantages like specialized equipment. Based on the comments and presentations, a plan of action was developed. In the feedback, the districts expressed concern on the difficulty they had collecting the information. It turned out we just didn't have the data in our bridge management system. So the data fields needed to be added, and since then they have been. Next, we had to update Pub 55, the Bridge Maintenance Manual. Under Section 3, page 14, we included epoxy and polyester concrete overlay. And the final step of our plan of action, we updated Design Manual 4, Section 5.6.4.1, Table 1. It was revised to include dual protection for bridge decks. The flow chart was updated to include the new materials. Keep in mind that the flow chart is a tool and it's not an absolute, so it might not be the perfect solution for your bridge. As you go through DM4, you'll find a list of the currently available preservation methods. We have sealers, membranes and bituminous, latex overlay with hydrodemolition, rapid set latex overlays with hydrodemolition, epoxy overlays, PPC overlay, and ultra high performance concrete overlay. They range in cost and complexity from simple and low cost to specialized equipment and very pricey. Which one's right for your situation depends on many factors. Lane closures and phasing, maintenance force levels of skill, and as well as your available budget. In the future, we hope to have additional materials in our toolbox. Materials like ultra high performance concrete and hybrid composite synthetic concrete. Both of these materials have shown promise bonding to existing concrete and making it composite. One last thing to mention, which is near and dear to innovation, is research. PennDOT is currently participating in a research study into bacteria that turns chlorides into carbonates. I don't have a timeline for this innovation, but it is showing some promise. Thanks for listening, and now I have the privilege to introduce our next speakers, Brian Miller and Shane Solankowitz. Brian will present on behalf of District 3, located in North Central Pennsylvania, while Shane is from District 11, and he'll be covering the region around Pittsburgh. Thank you.
Thank you, Tim. My name is Brian Miller, and I am the Assistant District Bridge Engineer for Design in PennDOT District 3. It's a privilege to be able to present our district's bridge deck overlay strategies and best practices as part of this year's Innovation Days. Today, I'll be giving an overview of two overlay types that we typically use: epoxy overlays and asphalt overlays. AASHTO defines bridge design life to be 75 years. PennDOT's design manual increases bridge design life to 100 years. Further, PennDOT's design manual states the expected bridge deck life to be 40 to 50 years. Funding levels will not allow for replacement of all bridges on a 100-year cycle or a deck replacement for all bridges on a 40 to 50-year cycle. Therefore, we must find ways to make bridges last longer. To reinforce Justin Bruner's bridge preservation presentation earlier, the only way we're going to extend bridge life and to move toward lower life cycle costs for all bridge assets is to invest in low-cost preservation work. Bridge decks are directly impacted by vehicular traffic, including plow trucks and salt applications, and are exposed to all weather conditions that we experience in Pennsylvania. The deck also provides some protection to the beams and substructure below. So bridge deck preservation is the key to reducing overall life cycle costs for bridges. The goal of a bridge overlay is to seal up the surface and to protect the structural deck from direct impact to the traveling public and from chloride contamination. The first deck preservation system that I will cover is the epoxy overlay, which is covered in Pub 408 in section 1046. The two materials are polymeric resin binder or epoxy and a fine aggregate. A quality control plan is required as outlined in Pub 408. The most important aspect to the construction of the epoxy overlay application is the deck surface preparation and cleanliness. The first step to surface preparation is to sound the entire bridge deck and to map out the unsound, deteriorated sections of the deck that need to be repaired. Type 2 deck repairs need to be completed. Our district specifies a rapid setting concrete. The patching material must be compatible to the overlay system being applied. In the case of epoxy overlays, the patching material cannot contain magnesium sulfate. Once all the Type 2 deck repairs are completed, the next step is to shot blast the bridge deck to remove all loose concrete, dirt, paint, oil, asphalt, and other materials from the bridge deck, and to provide an aggressive surface profile as specified in the International Concrete Repair Institute, number 310.2, concrete surface preparation level 5 to 7. Concrete surface profile chips are used to visually verify the surface preparation. Vacuums and air compressors may be used to remove all dust and loose material from the shot blasted surface. Pull tests are performed to determine the suitability of the concrete surface according to ASTM C1583. The minimum acceptable bond strength on normal concrete cannot be less than 250 psi. District 3 currently uses a special provision for the epoxy overlays. Our district has specified the use of bauxite as the aggregate is more durable. The special provision also specifies a minimum shot size and requires the contractor to pave the approaches prior to applying the epoxy overlay on the bridge deck. For cases where an existing epoxy overlay will be removed and replaced, the district uses a special provision to apply 3 layers of epoxy overlay instead of 2 layers. The bridge deck is scarified to make sure all existing epoxy is removed. The scarification is paid for using a separate pay item. Once the deck is scarified, the deck is shot blasted and a pull-off test is completed, followed by the epoxy overlay layers. This photo shows a contractor preparing the surface prior to the installation of the epoxy overlay. It is extremely important to make sure the deck is clean of all dust and debris after the shot blasting or scarification of the bridge deck. Many of the failures that we have experienced were a result of surface prep issues, including not getting the deck clean enough prior to the first epoxy application. The photo in the bottom left shows a prepped surface with an acceptable surface profile. The photo in the middle shows a scarified deck surface for the 3-coat system, and the photo on the right is showing the pull test on the prepped concrete surface. This photo shows the first layer of epoxy application running just ahead of the aggregate placement. A serrated edge squeegee is used to spread the epoxy uniformly across the deck. The aggregate is immediately spread onto the wet, uncured binder. After the first layer is cured, excess aggregate is removed by use of brooms, vacuums, or compressed air free from oil and water. The second layer is applied similarly to the first layer, and again the excess aggregate is removed from the binder has cured. Adhesion testing is again completed on the final layer according to ASTM C1583. Between 30 and 45 days of applying the epoxy overlay, the contractor will remove all loose aggregate from the bridge deck, scuppers, and expansion dams. This photo shows the final product of the epoxy overlay before the line paint is placed. One issue that the district has worked to address is the longevity of the overlay at the leading edge of the deck. Plow trucks damage the leading edge of the bridge deck if the overlay is not flush with the approach pavement. To provide a smooth transition from the approach pavement to the bridge deck, our district's special provision requires the approaches to be paved prior to the installation of the epoxy overlay. A best practice and a detail we have been adding to our plans recently includes adding a form at the end of the bridge deck equal to the 3/8 of an inch epoxy overlay thickness prior to paving. This allows the contractor to pave up to the end of the bridge deck and provide a nice clean edge that the epoxy overlay can be placed up against later. Once the approach pavement has been placed, rolled, and cooled, the form can be removed and the epoxy overlay can be installed. The second deck preservation system I'll cover is the asphalt overlay. Two different waterproofing systems can be used: a rolled adhesive backed membrane and an elastomer spray applied membrane. For this presentation, I'll focus on the elastomer spray applied membrane. Item 900680 covers the elastomer waterproofing membrane on bridge decks. The materials include a concrete primer, the membrane coating system, an aggregate, and tack coat. Bridge deck prep and cleanliness is also very important for this overlay system. Like the epoxy overlay, the first step in applying the asphalt overlay with an elastomer membrane is to sound the entire concrete deck and repair any deteriorated concrete. A pre-installation meeting is required, and the deck is shot blasted, a primer is installed, and then the membrane is installed. An aggregate layer is placed, followed by a tack coat, and then the asphalt overlay. Testing for the elastomer membrane includes a pull test in accordance with ASTM D4541 and also a check on the dry film thickness of the membrane. This check is typically done by measuring the yield of the material used. This photo shows the primer applied over half the deck. On the barriers, a protective surface is placed for overspray. The bottom 3 inches of the barrier will be covered with membrane, but the rest of the barrier needs to be protected for a nice clean final product. The procedure for the pull test is the same for the elastomer membrane as it is for the epoxy overlay. For the elastomer membrane, one set of tests is completed on the primer coat to test the bond strength between the primer and the concrete deck. 150 psi must be attained for this test. This photo shows the application of the 80 mil membrane to the bridge deck and bottom 3 inches of the barrier. After the 80 mil elastomer membrane is applied, a second membrane coat is applied and aggregate installed into the membrane before it sets. The second layer is between 30 and 40 mils, or as recommended by the manufacturer. In this photo, you can see the first 80 mil layer in orange and the second layer in gray as the aggregate is being broadcast. After the second layer of membrane and aggregate is applied, a tack coat is placed and the deck is ready for the asphalt wearing surface. In total, a 2.5 to 3 inch asphalt overlay is installed once the tack coat is placed. This allows for future milling and repaving as part of future paving projects. This photo shows the final wearing course on top of the elastomer membrane. And that will conclude my presentation. Thank you for attending this bridge deck preservation session. I can take any questions at this time. Thank you.
Hello everyone, I'm Shane Solankowitz and I'm the District Bridge Engineer for District 11. And today I'm going to talk about latex modified concrete and polyester polymer concrete overlays. But before I do that, I wanted to talk about structural bridge deck overlays. Can we consider latex and PPC to be structural? Well, back in 2013, we really weren't using PPC. We were heavy on latex, especially here in District 11. But at the time, DM4 did not consider latex to be structurally effective. So that was the importance of this study. The University of Pittsburgh took full-scale slabs to use for testing. They used AAA concrete in those slabs. That was the concrete that was for bridge decks at the time, that we didn't have AAA-P yet. And they took latex and they overlaid those slabs from depths from 1 inch to half the depth of the slab. And those results came in pretty good. So all the slabs behaved in a composite monolithic manner. Great news for us, right? And we had uniform capacity regardless of the depth of the overlay. So that was more positive news. And I think the most important thing that came out of that study was that we need a bond strength of 200 PSI minimum to consider an overlay to be structural. Now with PennDOT, we're always a little bit more conservative. So you'll see in our specifications that we want 250 PSI to consider an overlay to be structural. And because latex and PPC overlays provide that bond strength, they're both considered to be structural. And there's a lot of great benefits to that. Now, District 11, knowing that they're both structural, our best practice is to maintain deck elevations. Why not, right? Why increase the dead load if you don't have to? That's one of the big reasons why not to. But it also provides a more uniform overlay. It also saves cost of raising the dams and tapering the bridge deck ends. Now I'd like to move on to the latex overlay process with hydrodemolition. The first step being scarification. But before you scarify, you need to perform a survey of the bridge deck. Now the reason for that is, if there's any discrepancies on the amount of removal between inspection and the contractor, we will have that baseline to solve any of those discrepancies. That's part of the new specification for scarification. Now moving on to the actual scarification here in District 11, like I mentioned, we like to maintain our deck elevations. So to do that, our scarification process is 2 half-inch passes to remove 1 inch of the existing deck. Now, if you're a district that does not prefer to do hydrodemolition, you're required to remove in 1/4-inch passes. Now, the reason for that is, the milling operation, could cause microcracking in the surface, which could be detrimental to the bond. So 1/4-inch passes reduce that chance of microcracking. Now we like scarification, even with hydro. It opens up the deck surface for the hydro operation, and it really is an economical way to remove the top portion of the deck. The next step of the process is hydrodemolition. On the right, you'll see what a typical hydro machine looks like. You can see us in the background calibrating that machine. And what we do is we calibrate to remove a 1/4 inch of sound concrete to the peaks of the hydroed surface. So again, scarification removes 1 inch. We calibrate to remove that additional 1/4 inch to the peaks, and that gets us our minimum thickness. What that'll do, it will remove unsound concrete as well. the hydrodemolition process. And oftentimes the calibration for sound concrete will remove unsound concrete. We do test areas in sound and unsound areas just to make sure. If for some reason we need to do extra passes over the unsound areas, that's a necessary evil. But again, more oftentimes we do not. And what that hydrodemolition is going to do, it's going to provide a rough and bondable surface. One of the other things that came out of that pit study is they do recommend hydrodemolition to provide the best bond. So with that, because of that recommendation from the study, another District 11 best practice, again, is the hydrodemolition with our overlays with latex. It's going to remove the delaminations and it's going to give us the best bond. Here's another photo of a hydro machine as it's working its way across that deck. Here's another photo of a hydroed surface. Now this one has a lot more delaminations that were removed with the hydro operation. And what I was saying before is our goal here in D11 is to maintain the deck elevations. Now, if you were going to raise the deck elevations on this bridge, you'd be at least an inch higher. So that means the distance from the top of the new deck surface to the bottom of that patch would be deeper in those delam areas. So if we're going to maintain the deck elevations, it's more of a gradual taper into those delaminated areas. So the next step of the process is preparation. We want to perform any type 3 repairs before placing the latex. When you're doing the hydrodemolition process, I don't recommend using the hydro machine to remove all that material. Typically, we start to see that bottom mat of rebar. And if we start to see that, then we remove the rest of that material with 30-pound chipping hammers. Now, if you happen to have deeper type 2 areas, which are partial depth, if you have type 2s that exceed 4 inches, you want to place those before the latex. Both scenarios, you want to place those shy, so your overlay is still 1.25 inches. Next step is to calibrate the mobile mixer trucks before the placement. Then the contractor is going to water blast that surface no more than 24 hours before the placement, and then they're going to place polyethylene sheeting to protect the surface. The next step of the process is to place the latex overlay. On the right, you can see a mobile mixer with the chute. The latex is mixed in that mobile mixer, and the concrete is placed directly onto the bridge deck. But before we get to that part of the process, we want to make sure we wet the surface less than an hour before placement. Once we start placing, as we're moving along, we want to make sure there's no standing water present, so we want to vacuum any standing water. Also, as we're moving along before the latex is placed, we want to take some of that latex slurry and brush and broom surfaces that have not been hydroed. So if you did hydro, that's pretty much vertical surfaces, any phase joints, things like that. But if you chose to not do hydro, you have to brush and broom the slurry along the entire surface. And that helps with the bond. Just like any other type of concrete, we also want to vibrate the latex. And typically we're using a bidwell finishing machine, very similar to a normal deck placement. Now, one of our best practices here, and I know other districts look at it this way too, the more you work latex, the more you have a chance of tearing it. So what we like to do is let that bidwell finishing machine do the work for us. We obviously have to finish the ends or the sides at bulkheads, things like that. But the best practice here is to only repair any surface tears that may appear as you're moving along in the process. Now here's a photo of a narrow placement. You can see all the hand finishing on the ends. Again, necessary evil in a district like ours where we have a lot of high ADT and phase construction. But most of our placements are a little bit wider than this, but you can see we do not touch those areas in the middle, but we had to finish those ends. So the next step is curing. We want to use double burlap only. Previously, it was a single layer of burlap and plastic. We like to see that double burlap, and we talked to the latex industry when we updated the 408, and they were on board with it. They wanted to make sure that surface stayed saturated during the curing process because latex is vulnerable to cracking if you don't cure it properly and make sure it doesn't have any evaporation rate issues. With the cure, with standard latex, it's a 2-day water cure, 3-day dry cure. And if you have depths greater than 2 inches, you have to add an extra day of dry cure. With accelerated latex, we see that often here in District 11. It's a 3-hour cure. It's a 3-hour mix. So once you get 3 hours and you get that 3,000 PSI, you can remove the curing. And for us, it's been very successful for weekend placements. The next step in the process, pretty much the last step, is to mechanically texture that bridge deck. We talked about the minimum placement thickness of the latex overlay being 1.25 inches to the peaks of the hydroid surface. So how do we pay for the material that's below the peaks to the valleys of the hydroid surface in any type 2 or deeper areas that are placed monolithically with the latex placement? What you need there is a variable depth latex item. In the past, it's been a special provision. It's been incorporated into the 408, and there's a standard item for it now. And the best practice that we found here in District 11, with the practice that we have of maintaining deck elevations, is to estimate anywhere between 1 inch to 1.5 inches over the entire deck area for that additional material quantity. With that, I'd like to move on to the PPC overlay process. With PPC, the estimated overall removal depth is 1 inch minimum. And typically here in D11, that's what we go with, a 1 inch overlay. Now, the first step in the process is scarification. Again, we'll do the pre-construction survey or the pre-scarification survey, so we have that baseline. Now, a little bit different than latex, PPC requires a micro mill. Here in D11, we'll do 3 passes, 1 1/2 inch pass and 2 1/4 inch passes to get 1 inch of removal. Again, we're doing the 1/4 inch passes at the end to minimize the risk of micro cracking. Once the bridge deck has been scarified, we want to review the deck to make sure there are no more delaminations present. If they are, we have to go back and remove those with 30-pound chipping hammers. The next step of the process is shot blasting. We did the micro milling, and then we're going to do a shot blast, and that's going to remove any grease, slurry, debris, anything on that surface. We want a nice clean surface for a good bond. Once we do that, we move on to the prime coat. To put the prime coat down, the surface must be completely dry. Now, the prime coat consists of high molecular weight methacrylate. Say that 3 times fast. It took me a long time to get that one down. But for short, I like to call it HMWIM. A couple people are catching on to that. So if you ever hear HMWIM, it's high molecular weight methacrylate. And that is the primer for PPC. We also use that product to fill and seal cracks on bridge decks. It's a very good product. And it's the primer for the PPC overlay process. Put that on at a rate of 90 to 100 square feet per gallon. You got to avoid puddling, and you need to reapply if that HMWIM dries before the PPC placement. Now we're ready to actually place the PPC. You're going to want to set rails and use a vibratory screed. That's pretty much the way we've seen it here in District 11. You know, other states have used slip-form pavers. They've modified those for PPC placements. PPC is relatively new here, so we haven't seen that investment in our contractors here so far, but I think here in D11, it's a product that we're going to continue to use, so I think in time we're going to see that investment. But for now, we're seeing the vibratory screeds, and there's nothing wrong with that. We've had successful placements with it. They also use mobile mixers. You can see those mobile mixers mounted to that flatbed, those red mobile mixers in the photo on the right. They have pre-proportioned materials. They dump in those mobile mixers, and they dump the PPC onto the surface. Now, you want to make sure you're placing that PPC after 15 minutes and within 2 hours of the HMWIM application. Then you're going to go ahead and finish. You can see our finishers there. They will float the material. They can hand finish. It's not like latex where you're concerned about that. And then once it's finished, we're going to go ahead and broadcast sand. The photo on the right here, you can see some of that broadcast sand. But the next step is curing. There's really not much you have to do there. With the curing, there's no wet burlap or any sort of plastic or any sort of curing. It's just not necessary. So what we do is after about 4 hours, that's typical for PPC to cure, you want to use a Schmidt hammer to check the compressive strength about every 10 feet across that bridge deck. Again, it's going to cure in about 4 hours, and you'll be able to open to traffic. So very similar to 3-hour accelerated latex. This is very good for weekend operations, especially if you have high ADT in sensitive areas. And like latex with PPC District 11, we prefer to mechanically texture it. Now here is a photo. This overlay here was tined, but in D11 we've moved forward with mechanical texturing. Moving on to some differences between latex and PPC. First thing being permeability. First, I'd like to say, AAP is our standard bridge deck concrete. It's not to exceed 2,800 coulombs. Now, what's a coulomb? I don't know. Take a look at the chart on the right. All I know is the lower the coulombs, the better, right? So with 2,800, we're sitting there in that moderate range. And, we've done a lot of work on our AAP mix over the years, and that's pretty much where it is. I would like it to be somewhere around 2,000. But we know realistically it's about 2,800. Now with latex and PPC, we get a much better permeability rating here. So with latex at about 28 days, we're about 2,500 coulombs. Now that's in the moderate range, but over time, that's the thing with latex, it coalesces. And in about 6 months, you have about 700 coulombs, and it gets you in that very low permeability range. Now, a PPC, it's off the charts. I mean, it's less than 100. That's what makes this material so intriguing, and that's why a lot of people are very interested in using it. But with that said, both materials are still very low in the permeability range. Next differences here, bond strength. Again, the minimum requirement here to consider something to be structural is 250 psi. Now with a hydroed surface, on average, we get about 400 psi, so we're exceeding that, no problem. I don't have too much experience with latex overlays without hydro. I would assume it's a little bit less, but we know that some districts have had success without hydro and are meeting those requirements. With PPC, the bond strength is a bit higher. It's about 800 psi, and to me, the higher the bond strength, the better. But again, both exceed the 250, so both are great products. More differences, compressive strength. Now, for both materials, we want 3,000 psi in order to open to traffic. Now, latex at 5 days is about 5,000 psi. Now with PPC, I had to take a look at this. I know we get at least to 3,000 in 4 hours. I'm not quite sure what this 7,000 psi is. Is that 28 days? Is it 5 days? I know the data sheet for the material that's in the bulletin is 7,000 psi, but I'm not sure the duration. But what I'd say about both of those, they're pretty similar for compressive strength. The next difference here is unit weight. Latex is about, like standard concrete, 150 pounds per cubic foot, but PPC is a little lighter. It's 135 PCF. So very slightly reduce the dead load with PPC. Now with construction joints, latex, if you have phased construction or anything like that, you got to seal those joints. Now the current standard is to saw and seal those. In District 11, we've moved away from that. We place our phases flush, and then we use HIMWIM to flood. We want to flood those cold joints and construction joints between the two, instead of opening up that joint with a saw and filling with that bonding compound. Now with PPC, as you saw in the photos in previous slides, we were doing a lane at a time and a shoulder at a time. And the reason for that is you could do it because that material chemically bonds to itself. So you can have adjacent placements without worries of any sort of construction joints. Moving on to some more information about latex versus PPC. So the PPC overlay, it is very similar to a latex without hydro, to where you do have to review and sound the deck after scarification to make sure you got all the DLAMs before you overlay it. Another thing is coordination and preservation work. Now with PPC, you have to wait 28 days to prepare in place PPC on new concrete. That's not the case for latex. You really only have to wait until that concrete is 3,000 psi. Now with that, with both processes, you got to wait for 3,000 psi minimum to be able to scarify in hydro. So that's the minimum amount of time. However long it takes you to get to 3,000 psi is when you can start that operation. If you have new concrete, like in expansion dam blockouts, any sort of deck repair. So you need to schedule that work accordingly. A couple more best practices in D11. When we have expansion dam blockouts, We may place those to grade and then scarify and hydro those. If you have a longer closure, maybe you place those expansion dams shy, the blockout concrete shy, so you can overlay to the extrusion. But one thing we never do is here in D11, we do not like to overlay back walls. We don't want to have a thin strip of overlay on a very narrow back wall. And we found that we typically get some delams there prematurely if you overlay. So when we do expansion dam blockouts, we carry that new concrete to grade on the back wall side. So, with these overlays, we've talked about it, other presentations have talked about it. We really have a cycle maintenance strategy. I mean, I just went through all the processes and how we place these overlays, but why are we doing it? It's really because of this cycle maintenance. We want to preserve our bridge decks as long as possible. So with latex, a difference here in how we use those products here in D11, it's kind of changed a little bit now that we have PPC. Latex is more of a bridge deck rehabilitation. We want to perform it on bridge decks rated greater than 4, and it's it's better suited when more delaminations are present because you're going to do the hydro operation. You're going to use that to make sure all the delams are gone. So typically we use that on a bridge deck that's a little bit older and needs to have those delams removed. We're typically not using it on new bridge decks here in D11. I know some districts have had a lot of success. There's nothing wrong with using latex on a new bridge deck, but for us, again, we want to get the best bond and we want to hydro. We typically don't want to hydro a brand new bridge deck. That's just our philosophy here. Now, the life cycle of latex is about 20 years. Now, if you put it on a new bridge deck, it's probably going to last longer. Typically here in D11, we're putting them on bridge decks that have been around for a little while. And, sometimes we push the envelope and get 15 years. Sometimes we get 25, 30 years. But on average, we get about 20 years on our latex. Now with PPC, the philosophy here, just like latex, but with PPC, we want to keep good bridge decks good. Bridge decks with less delams, we want to keep them with less delams. So we like to use it on newer bridge decks, interstate, high ADT, difficult to access. That's where we want to target PPC. It's a little bit more expensive than latex, so we want to make sure that we're using it in the right place. And maybe as time goes on, the cost is going to come down. So again, use it where there's minimal delaminations present. And right now, we believe the life cycle is 30 years. That's what we're hearing in other states. And we haven't had that material that long here to prove that, but we've had some testimony from other states. So we feel it's about 30 years. And again, most likely because we're placing it on a newer deck and you have a better chance for an overlay to last longer on a newer deck. Building on the previous slide, the D11 strategy for latex is for bridge decks with more delams, something that needs more of a bridge deck rehabilitation. So the photo on the left shows just that. After the hydro process, you could see all the delams that were revealed. You could see a lot of the exposed rebar there. Now the photo on the right is the exact opposite. I mean, this bridge deck was built in the 80s, I believe, and honestly, it's in great shape. We did latex it, but it would also be a candidate for PPC. So again, the photo showed 2 good candidates for latex, but the photo on the right would be a better candidate for PPC. Now the reason for that is we know the cost of the PPC material is more than latex. So what triggers me to use latex is if I know I need to hydro the surface to remove some delams, I'm knowing that it's a better candidate for latex than PPC. Now, to build on the previous slide again regarding where to use PPC, again, we're targeting high ADT roads, new bridge decks on high ADT roads, preservation on our better bridge decks on high ADT roads, urban areas, congested areas, difficult to access areas where you don't want to have to install traffic control. And we're choosing PPC there because we know, although it costs more, it has the lowest permeability, and it gives us a better chance for that overlay to last longer and preserve that bridge deck longer. And if it does last the time that we think it's going to last for 30 years, we think we will be able to go in and mill and fill and replace that PPC overlay. So with that, that's the process with latex and a little bit of the cycle maintenance strategy. So I'd open it up to questions.
Hello, everyone. I'm Dennis Neff with the PennDOT Central Office. Thank you for joining me today for a discussion on an innovation that we call geosynthetic stabilized bridge approach. This is the outline of the discussion today. I'll begin by talking about the problem that the innovation addresses, namely bridge bump. Talk about what bridge bump is and why it happens. Then I want to talk about specifically the innovation itself, what it is, why it works, where it's been used, and finally, some cost and benefit information. To gain perspective on the problem, let's first realize that there are approximately 600,000 bridges in the United States. And previous studies have shown that approximately 25% of those bridges suffer from bridge bump. The repair of such problems is also estimated to cost approximately $100 million per year. We translate those numbers to Pennsylvania. For our 25,000 plus bridges, we could expect approximately 6,000 of those bridges to be suffering from bridge bump. That equates to approximately 100 to 120 repairs annually at a cost of $20,000 to $120,000 per bridge. Now let's take a look at what the bridge bump problem looks like from the surface. If you take a look at the photo on the left, you look closely at the white line on the right-hand lane and follow it towards the bridge, you'll notice a slight depression right before the bridge begins. That's a telltale sign of settlement at the end of the bridge. Now, this may not look like much from this photo, but driving over a bridge like this and an approach like this, we would definitely notice the settlement. We would hear it and we'd most likely feel it in the suspension of the vehicle. On the right hand picture is another example. It's much more visibly evident. Again, you'd hear this and feel it as you drive over it. Here's another example of what approach settlement may look like in the more advanced stages. In this case, a maintenance crew may come out and attempt to repair this on a periodic basis. The fact is, the ride quality never is reestablished to a like-new condition, unless a very aggressive repair effort is undertaken. Now that you have a good idea of what bridge bump looks like at the road surface, let's take a deeper look and try to understand what's happening below the road. In this depiction, which is a cross section approximately at the center line of the road, we can see that the bridge abutment is shaded green. The backfill of the abutment is shaded in orange. Notice how the backfill directly supports the approach slab and approach pavement. This orange zone is typically the most suspect when it comes to settlement. You may ask, what is the degree of settlement? What's the magnitude that really causes a problem? As depicted in the table on the bottom right corner of the slide, you'll see that it doesn't take much more than an inch of settlement to really start becoming a problem. It's important to understand that there's not just one single cause of fill settlement or loss of fill near a bridge. This diagram identifies 15 different potential causes of settlement or loss of fill. Once we understand that, we also know that there's probably not just one solution to solving the problem, because there are so many potential causes to the problem. That is the point of this slide, to gain perspective on just how complex this problem is, and why so many researchers and engineers and DOTs have been working to address the problem for so many years. The takeaway might be this, that the bridge approach, and the roadway are a dynamic environment. There are many stresses involved: thermal stresses, heating and cooling, moisture stresses, wetting and drying. And of course, gravity is always at work. So it became clear what we needed to do was identify a cost-effective solution to reduce bridge approach settlement. After all, is a cost-prohibitive solution really a solution? As it turns out, GSBA is the effective, affordable solution we've been looking for. Now I want to look at what the GSBA actually is comprised of. And to do that, we're going to look at another cross-section. This time you'll note that the abutment, the bridge structure, is shaded in green. The pavement or approach slab is depicted here shaded in yellow. But notice the difference, that the fill below the pavement is now reinforced with a geosynthetic at regular intervals at a depth of approximately 5 feet below the subgrade. This differs considerably from the other depiction, where it's simply aggregate used as backfill. The lower cross-section shows the lateral extent, left to right, of the roadway approach embankment, and how the layers are terminated with wraps at approximately the location of the guide rail. You can see the approach pavement is fully supported by the reinforced fill zone. As you can imagine, Pennsylvania isn't the only DOT with an interest in solving the bridge bump problem. Several years ago, Tennessee DOT funded a research study that looked at the application of geotextiles in the bridge approach fill. As depicted here, a finite element model was used to examine the stresses and the potential settlements averted from including geosynthetics in the fill. You'll notice that Tennessee's detail looks very similar to what Pennsylvania is attempting to adopt as a standard. This is no coincidence, as we looked very closely at the Tennessee study in determining what the optimal spacing and depth of the reinforcement should be for our standard design. Well, that's as technical as we're going to get during this presentation. Now let's take a look at how the GSBA is actually constructed. And it really is rather straightforward. Once the bridge is constructed to the point where it's ready to be backfilled, the base of the embankment is prepared. And as shown in the photo on the left, the geosynthetic reinforcement is placed. Next, a layer of aggregate is placed, as shown on the right-hand photo. After the layer of aggregate is placed to the correct thickness, it is compacted properly. Now, I said the construction was straightforward, but that doesn't mean that it cannot be done in an incorrect manner. It is important to have the aggregate well compacted. It's also important to have the geotextile placed in flat layers in the proper geometry. Now, our final specification may look a little different than what's shown here in this picture, because the end wrapping has also been added. But the general idea is the same. This process is repeated until the embankment reaches the planned subgrade elevation. As mentioned previously, technical research has shown that this innovative construction technique is effective. Not only that, Pennsylvania and other states have actually constructed these types of structures and have proven that it is effective. Since 2015, PennDOT has constructed over 50 GSBA structures. These have mostly been located in Districts 2 and 11. To date, all GSBAs are performing well, with no approach settlement correction needed thus far. We believe that it has been technically and practically demonstrated that this innovation works. And we're moving forward in implementing a standard design detail. Finally, let's take a look at some cost benefit. What we're essentially doing is comparing preventative measures to repair costs. Recall from a previous slide that we're estimating PennDOT has about 100 to 120 bridge bump structure repairs annually. If we anticipate that the GSBA could prevent at least 50% of these repairs, and we also estimate that the GSBA construction adds about $5,000 in additional cost to the standard bridge approach construction, and we anticipate that conventional bridge bump repairs cost on average of about $35,000. We can do some math and determine that the annual potential maintenance cost savings may approach $3.5 million. But there are bonus benefits in addition to the direct cost savings, one of which is improved safety. If we avoid the need for work zones to repair settled approach pavements. And secondly, the improved customer satisfaction by having smoother roads. Now, those bonus benefits are difficult to quantify in a monetary sense, but they are very real benefits. That concludes my presentation. Let me just end by mentioning we are currently developing a new roadway construction standard, RC15, that will be housed in Publication 72 to become our new GSBA design standard. This is initially going to be an option for roadway and bridge designers to use on their projects. Thank you for your attendance.
Hello, my name is Jonathan Moses, and I'm the District Geotechnical Engineer at PennDOT District 11. Today I'm going to be talking to you about an innovation known as deep soil mixing for landslide remediation. The specific project I'll be talking about is our SR68B41 Midland Road slide repair. Deep soil mixing is a ground improvement technique that improves soft, high moisture clays, peats, and other weak soils by mechanically mixing them with a cementitious binder. So you have the existing material, subgrade, and you're mixing cement with it at a known rate to achieve specific strength results. You're basically strengthening that soil by mixing it with a stronger material. The case study is our State Route 68 project in Beaver County, Pennsylvania. It is western part of Beaver County along the Ohio River near the Ohio and West Virginia border. One of the challenges we had is exactly where our state road was located, since it was right next to the Ohio River. This slide shows the estimated limits of the slope movement. You can see that the upslope was moving as well as the state highway and the railroad all the way down to the Ohio River. It was a pretty long area that was affected. This slide shows some photographs of the effects of the landslide. On the left, you can see the railroad's lines and how wavy their tracks are. They had to come in every couple of weeks and reballast their lines just to keep them operational, as well as having a speed reduction down to 10 miles per hour that's been in place for a number of decades. On the right, you can see the state road. So you can see the hole in the pavement, and the hole in the pavement here, and there was a number of holes in the pavement that were in a line, and that is basically where the scarp was. So the pavement was sinking and pulling away from the cut lane in that area. This particular photograph shows it down to a one-lane closure controlled by temporary signals, and that was put into place shortly after we were called out there on July 4th of 2018. Okay, this is a geotechnical cross-section. This dashed red line shows the center line of State Highway 68. Down here is the railroad. Down here is the Ohio River. You can see here that the colluvium and alluvium layers are about 45 to 50 foot thick before you hit bedrock. Oftentimes in District 11, we have anywhere from 10 to 20 feet or so before you hit bedrock. That lends itself pretty well to your typical soldier pile walls or geosynthetic reinforced soil slopes, things of that nature, or even a rock slope. But here, the failure was a lot deeper, and we had both of these layers of pretty weak material before you hit bedrock. So we didn't really have our normal tools of the trade to respond here. The railroad actually approached us a few years back wanting to do some type of joint project where I think the solution was some type of wall to stabilize this landslide. And throughout the corridor, it was estimated this wall was going to be $50 million, and they wanted to cost share with the department. So even assuming $25 million, that was a lot of money that the state didn't want to have to pay. So they were looking for a solution to the problem out here. So that's where the innovation came into account. The photograph on the left of this slide shows the thickness of the pavement out there after we milled and excavated down to our working platform elevation. The holes that were shown on a previous slide, were up here at the top of the pavement, where down to grade we have over 5 foot of asphalt in this location. So our forces went out here and paved time and time again to try to remedy the situation, and that would be okay for a year or two, but then it would sink again and the crack would open up. So most recently it was deemed that the amount of damage that we were seeing out here, and just like how uneven the pavement was and what that was doing to the truck traffic out here, it was deemed to be, let's find a solution out here that's going to be long term, that we can fix this problem instead of just band-aiding it every couple of years. So we did ask for emergency funds, and were granted those funds to address the situation long term. A photo on the right is a 7-foot flight auger. You can see someone's boot there in the photo for scale. So that was a 7-foot long auger that was doing the mixing of deep soil mixing. In the center of the shaft, there was an opening where the grout was pumped in. So it was pumped from up top above grade down through this auger as it was mixing the soil. This is a plan showing the limits of the deep soil mixing. Deep soil mixing was done just below the roadway towards the railroad tracks, and it was about 400 foot long, a little over 400 foot long section that we were doing the deep soil mixing. Here is a cross section showing the center line of our road, and just past the shoulder, underneath the shoulder back up is where those deep soil mix columns were. You can see a 20 foot width by 3 foot thickness. So basically the rectangular cross section was what made up these panels. So these panels were 3 foot wide, spaced at 4.5 feet, clear spacing. So we needed to leave that spacing in there so that water could infiltrate the soil and go through those out towards the river down below. Another part of this project is we added drainage to the cut side to try to drain some of that water out of the subgrade and get that out of there. We then had some cross piping at finite locations, collecting that drainage and getting it out of the subgrade through the panels down towards the river. The sketch on the bottom left shows the idealized panels, being rectangular in cross section. How they were actually achieved in the field was circular columns. Those are 7 foot diameter columns that were drilled. They would drill the first one, so column A, they would come and drill column C, then it would come back and do B, and then finally do D. So that is how they achieved those panels, was 4 circular columns drilled in a line so that those would make up those panels. And those were 7 foot in diameter, and they were spaced at 13.5 feet on center. So that was looked at as a similar replacement of material, or actually probably a little bit more material was replaced. Overall, a higher percentage in the overall project limits. And on the right, you can see a photo of the deep soil mixing taking place. That flight auger, that 7 foot auger, is down below grade, and it would mix that around and come back up and go down until you had a good mix there. Here is a picture of the grout plant. You can see these large containers. They contain Portland cement. Mix that with a certain amount of water, and then that would get pumped from the grout plant here about a mile down the road where the actual deep soil mixing was taking place. On the left, this is one of the controllers where you can see where the depth of your auger was, how much grout you're adding, what the flow of that grout was. So they had a lot of quality control out there to determine just how much they were pumping, if they were meeting what they were thinking they were, and their production rates and things of that nature. Here's just a printout of the daily reports that we received. Most importantly, what we used the most was the red line. So it starts at 0, which is grade, and goes down to about 50 feet or so at the top of a rock. So you can see that auger went down and came back up, went down further, came back up, down, came back up. So what that is showing is that the auger would go down a few feet, mix, and every once in a while it would come all the way back up to the surface and then go down. That's so you're not just getting a good mixture at that particular depth, but also vertically you're getting a good mixture, up and down in those deep soil columns as well. The other lines are the grout flow and the rotation of the auger itself. This slide shows a daily report, just an example of one that we would get. Some important things to note on here. The strength that we were looking for was 115 psi. And you can see the 7-day and 14-day strengths respectively for these samples that were tested on this particular day that were available. You can see the 28-day was not available because the 28 days had not passed. You can see the 14-day was not available for some of these because 14 hasn't passed. So this is just a snapshot in time showing what samples were mixed, and if enough time has passed, what those strengths were. How we were able to obtain these, we actually got wet grab samples. So what that consisted of is there was a little box kinda and that was mounted to the end of the auger. So at certain times, after it was sufficiently mixed, that box could be controlled and opened and would grab a sample of that material below grade and close itself. And then when that was brought up to the surface, that material could be taken out, and that sample could be stored and tested later on to see what that strength was. And these are just tabulating those results. So for this particular sample, 35C, so that's one of those circular columns in row 35. It shows you the target addition of the Portland cement, the water cement ratio, and the depth that was being mixed. That was 10 feet depth. That same column, 35C, the lower depth, the next 35 feet was alluvial material. It gives you a different Portland cement addition rate there. Didn't need quite as much Portland cement in that particular layer. So kind of to summarize, okay, what we're mixing, what our targets were, what we're actually getting, and then the results of the breaks for each of those layers. So that's kind of how they did their quality control, and that was a good way to represent it to us to see what strengths they were actually getting for those different layers. We also had a certain number of verification cores called out in the contract. So after the columns were mixed and set up for a sufficient number of days, we could bring in a typical drill rig, bring our 2-inch diameter core boring type bores out here to do cores. So the contract specified 2 different requirements. One was that strength that had to meet the 115 psi, but the other was also it had to be mixed well. So it was more of a visual thing. So if you look at this core and you saw a specific area that was like a handful of gravel or something, you would say that's not mixed well enough. We need to redo this or add a column or something. So even if it passed the strength, that could be on a section here that is mixed well, didn't necessarily mean that every finite section was mixed well. So it had to meet those visual mixing requirements as well as the strength requirements. So as far as cost benefit goes, I mentioned earlier that the railroad had their engineer had specified a $50 million wall throughout this corridor. So even if you take half of that, if we were going to share costs or something, that would be $25 million. The cost of this project was in the ballpark of $3.5 million. And I'm only really presenting on the one slide. There was another slide area that we did not do deep soil mixing, that we did some excavation and regrading and things of that nature. It was a little bit different geology there. But for the whole corridor, they estimated $25 million would be our share of building this wall. We did this whole project for $3.5 million, so we were pretty happy about that. There was a great savings, mainly due to just how deep and how beefy a wall you'd have to put out here to get it to work. There really wasn't a good solution on a structural sense, so that's why we turned to one of these alternate technologies. As far as lessons learned and best practices, what you need to put in the contract are specifications on how well you want things mixed, what strength you want to get, when you need things tested, what you want them to present to you, so that your inspectors know what they're looking for each day. So the contract tells you, here's what you need to look for up front, and then as the project progresses, your inspectors know what to look for each day. Like, oh, we have to have these strengths, we have to have this certain amount of cement that was mixed, or whatever. They need to have something to look at out there, because this was a special provision. It's not like a standard item in our publication 408. So our inspectors are very familiar with that. Once a special provision, all those things need specifically called out so they know exactly what to look for, so that you're getting the quality control that you need out there. Other than that, if you have any questions, my contact information is here. I'd be happy to discuss this further with you, or to provide you, any additional resources that may help you if you're looking into this type of technology. Thanks for your time.